I'm Dr. Shelley Cooper, and this is my lab report. Velocity is a vector quantity. Two components are required to describe velocity: the speed of the object, which corresponds to the magnitude, and the direction of the object. In order to have constant velocity, an object must travel in the same direction, and it must travel at a constant speed. A key assumption that is made for the case of constant velocity is that the sum of the forces on the object, things like the force of gravity and the force of friction, are zero. This is not to say that each individual force itself is zero, but that the net or total forces on the object equal zero. Newton's second law is the equation used to calculate an object's velocity. The final velocity is equal to the initial velocity plus F net divided by the mass times delta t. If we do some algebraic manipulation of this equation, say getting the object's mass out of the denominator of this fraction, we end up with the following equation. Mass times velocity final is equal to mass times the velocity initial plus F net delta t. Mass times velocity is a vector, and for the purposes of this course, this vector is the momentum of the object. The symbol used for momentum is p. Substituting p for mv in the above equation, we can see that the momentum of an object at time t is equal to the momentum at time zero plus the product of the net forces times the time interval chosen. You'll notice that when we make the assumption that the net force on the object is zero, we can eliminate the second term in Newton's second law. It becomes simply the velocity at time t is equal to the velocity at time zero. This makes it easy for us to determine the position of the object at time t is equal to the initial position plus the product of the velocity times the time interval. Moving on to the actual experiment, instead of rolling a ball, I decided to use a different object for my experiment. This is Luigi. He stood in for the ball. Why did I do this? Number one, Luigi is cute. But number two, if all goes well, I'm hoping that his powerful engine will overcome any other external forces, ensuring that F net is equal to zero. My assistant Penny drove Luigi past my camera, attempting to maintain a constant speed of 10 miles per hour. I took a video with my iPhone and then I analyzed it using Tracker. I set up a coordinate system which would provide a reference point for the direction of the velocity vector. On this coordinate system, the positive x direction is toward the right of the picture, the positive y direction is toward the top of the picture. Luigi and Penny are traveling in a straight line in the negative x direction on a level surface. Thus, the x and y components of the velocity vector are both zero. I obtained the velocity data that can be seen in the graph and table to the right of the screen. Then input the data I obtained into Python, the program used to predict what Luigi's constant velocity should have been. Initial velocity was calculated by dividing Luigi's change in position over the first time interval by that time interval. There you have it. That turns out to be 4 meters per second, and the vector that we're going to put into Python is -4, 0, 0. Here we can see the changes made to the provided Python code. We've added Luigi's mass, we've changed the ball position vector to the origin, and we've changed the velocity vector to -4, 0, 0. I've also changed the time to the total time of the experiment, 2.167 seconds. Here we can see that Luigi was moving in the negative x direction at a nice steady rate. The graph generated by Python indicates the same thing. The data from the experiment and the values predicted by the model were graphed using Google Spreadsheet. Our experimental data wavers just a little bit, but basically it follows the line of the model prediction fairly well. This indicates that Penny was successful at maintaining a constant rate of speed during the data gathering time. Now it's time for some what-if scenarios. What if this Ewok suddenly beamed down right in front of Luigi? Obviously, Penny would throw Luigi into reverse back down the street at a constant rate of speed in the positive x direction. Luigi's velocity vector in the Python program will now be changed to positive 4, 0, 0. Here we can see Luigi is moving in the positive x direction. What if General Tom Stafford, the astronaut who commanded both the Gemini 4 and the Apollo 10 space missions, stepped out into the street? Penny would jump out and say hi. To model this in Python, Luigi's velocity vector must be changed to 0, 0, 0. Here we can plainly see that Luigi is going nowhere.